All right, so welcome back. Hard to believe classes were canceled last week because of snow, but glad to see everybody back here. So what we're going to do today is we're going to finish up our look at Chapter 2 by taking a look at the last concept introduced in that chapter, which is z-scores. So we already took a look at measures of central tendency, and we discovered the mean. And then we saw that we used the mean in our calculation of variance and standard deviation. And now we're going to see that we're going to use both the mean and standard deviation in our calculation of a very useful concept in statistics, which is z-scores. So before we get to that, just want to remind you that our exam is coming up. It's been moved back a week. I didn't have a chance to update these slides. But just to let you know what's going to be going on, it's going to be on chapters 1 and 2. So frequency distributions, and then the mean, variance, and today's z-scores. And it's going to be a completely computational exam. So it's going to be done in Excel. Your Excel sheet will be available through Canvas. So once you come in class, and it must be done in class, once you come to class, sign in to your Canvas account. It will pop up and become available at the beginning of the class at 11:30. There's going to be 7 questions in total, and it will not be a surprise what any of those questions are. So you will have questions on everything that we've covered in the lectures. So order of operations. There will be a question on order of operations. There will be questions that test your ability to use the summation function. In terms of frequency distributions, there will be questions that test your ability to read a frequency table and read a frequency graph. So you won't be making tables or graphs, but you will be looking at tables, looking at graphs, and then answering questions about the data that they summarize. There will be questions where you need to calculate the mean, the median, and the mode. There will be questions where you need to calculate the sum of squared deviations, standard deviation, and variance. And then finally, there will be questions where you need to calculate z-scores. And as we see today, you can go from raw scores to z-scores, and then go back from z-scores to raw scores, and we'll be doing that also on the exam. So we'll cover that part today. And just a reminder, because this is the first one, it will be open book, by which I mean open everything except other people. So as long as it's your own work, feel free to bring, so let me rephrase that. As long as you're doing the work by yourself in class, feel free to bring whatever you feel you need in order to accomplish this exam. So if you want to make notes for yourself, step-by-step guides prior to the exam and bring those in to jog your memory, fine, completely acceptable. Canvas will be available to you. MyLab will be available to you. You can look at the lecture notes. You can look at your own notes that you've made, the textbook. You can even Google stuff if you want to. Everything is available except other people. So cell phones will be put away, no Skyping with anybody else. And I encourage you to take advantage of this open book policy, because the idea is that you're not memorizing formulas or memorizing equations, but you're learning how to do things. And if you're at the stage where you need some sort of external resource to sort of guide you through that a little bit, that's completely acceptable. The one warning I will give you is that open book will not work if you're trying to learn the material during the exam. So on the exam day, if you can't remember after today the formula for a z-score, write it out. Absolutely fine. So that when that question in the exam comes and you say to yourself, oh, I have to calculate a z-score, what was that formula? Oh, here it is in my notes. Okay, this is what I need to do. That's the way to use the open book policy. The way not to use it is to get to that z-score question and say to yourself, what is a z-score? Let me look at chapter 2. Let me read that section for 30 minutes and try to figure out what I'm supposed to do here. So come prepared, but definitely bring any resources that you think you might benefit from in this exam. All right, so prior to the exam, next class, February 7th, we're going to have a review session. So this is going to take place before every single exam. This is your last class session to basically ask any questions that you have in order to get prepared for the exam. So it's going to be an open review session. What that means is it's student driven. So I will have nothing prepared in advance. I won't have any sort of material that I want to go through, but it's your hour and 15 minutes to basically just put up your hand and say, can I see how to calculate standard deviation one more time? I've been practicing my z-scores and they're not working out. Can you go through that once more? Whatever you need to get prepared, it's going to be, you can have that in the open review session. Because of that, it's also completely optional. So if you feel your hour and 15 minutes would be better spent preparing in another way, absolutely feel free to do that. But if you do want to take advantage of the review session, I'll be here for an hour and 15 minutes. Bring any questions that you might have, and we'll make sure that everybody's ready to go. All right, any questions about that? So do check the post-snowpocalypse syllabus for your updated due dates. I updated it in my lab so that the due dates are now have been adjusted, but also double check with the syllabus because again, the exam is going to be a week from today. And while we're on the topic of Canvas, because this course uses a lot of pre-tests, a lot of post-tests, and has fewer exams, and because those exams are on a sliding scale, Canvas is very poor at calculating your grade as you progress through this course. So what I've done is in your Canvas gradebook, I've made every assignment that I post there not included in the calculation of the final grade in Canvas. So first off, do not be fooled. It still counts towards your final grade. It's just I wanted to remove that option in Canvas where Canvas is calculating your final grade. What I have done is I have uploaded a projected final grade tab that is 100% of your grade in Canvas. So that's where I take everything that you've done, all the pre-tests, all the post-tests, all the assignments, I've uploaded them into my Excel sheet. I've used the formulas to weight everything the way that it's supposed to be weighted. And the projected final grade is basically how you're doing at this point in the course. And if you continue at this level of performance, that will be your final grade in the course. So that's just a way of you knowing kind of how you're doing in the course without pre-tests getting overweighted or exams being incorrectly weighted in that case. So check on that. Make sure that you're doing what you need to do, and that's your kind of where you're at in the course right now. And on that note, also your individual scores for things like pre-tests will also be posted in Canvas just so you can double check. And the pre-tests have been updated for people's mastery points that they have completed as of, I believe it was noon yesterday. So you still have time. You have until the exam to complete any of those mastery points. But just so that you kind of know where you're at right now, I've adjusted it to take into account the mastery points you've completed up until yesterday. So if you believed that you completed 100% of the mastery points and you check your pretest and it's not 100%, that indicates that you missed some. So just double check that to make sure that it's reflecting your progress. All right, on to the new stuff. So this is one of the most fundamental pieces of practice that we're going to be doing. So this is one of the most basic, we need to get this down concept today with z-scores in order to do the really cool things that we're going to be doing later on when we're taking a look at actual psychology studies. This is one of the last kind of items that we really need to practice, really need to get down. And I will kind of give you a little bit of a foreshadowing. Z-scores tend to be one of the first areas that if you're going to struggle in this course, this is probably going to be the first part where you will. So I've just noticed teaching this course before, about everybody understands frequency distributions, about all the students get central tendency, about all the students get standard deviation, but some of them struggle with z-scores. That's your first hurdle. So if that's you, Number one is completely normal. Don't think that you're, losing the bigger picture. But number two, do make sure that you continue to work at it until it makes sense, because Z-scores and things that are like Z-scores are going to be used throughout this entire remainder of the semester. All right, so what is Z-scores? Well, let's take a look at where a Z-score might be used in a real life situation. So let's say that you are a clinical psychologist and a mother comes in one day and she has a child and she needs help because of behavioral issues with that child. So she comes in and she says, my child seems to be very active, almost hyperactive, right? Bouncing off the walls, bouncing off the ceilings. I just can't get them to sit down and not be active. And then also, she mentions that they have something else. They also have trouble paying attention and focusing. So you can diagnose this individual, and if there are two separate issues that an individual is dealing with, if there's comorbid issues such as hyperactivity and an attention deficit, often the best way to approach this is to approach the issue that is the bigger problem first. So as a psychologist, you would want to have a system where you could measure the amount of hyperactivity and you could measure the deficits in attention and determine which one of those is the most extreme behavior, which one of those is the bigger problem, and start with that one first. Now, this is going to be a challenge because they're measured on different scales, right? You would have a scale for hyperactivity, you would have a scale for attention. And the question that we're going to answer now is, how can you compare those two scores so that you can determine which one is the bigger issue so that you can have an effective treatment? So we're going to do all that with Z-scores. So first we're going to introduce the idea of Z-scores. Then we're going to take a look at how to calculate Z-scores. We'll take a look at some of the properties of Z-scores. We'll take a look at how to go from raw scores to Z-scores, and then how to go back from Z-scores to raw scores, and talk about a standardized distribution. And then I'll mention the homework assignment for the Z-scores, which is a special homework assignment not available on my lab. It's available in the Excel homework sheets in Canvas. All right, let's introduce these Z-scores. So imagine that I was that clinical psychologist and I developed a test to determine a child's activity, and much like an IQ test, I call it active Q. So it's the active quotient. And that client that came in, his name is Jimmy, and let's say that he scored 80 on my active Q score. The question we need to ask is, what does that 80 mean? So without knowing what that active Q score is, or without knowing what that active Q test is like, we have no idea if that's a high active Q. And we have no idea if that's a low active Q. So if you came up to me and said, oh, what was Jimmy's score? And I said, oh, it was an 80. You have no idea. Is that high or is that low? But the one way that we can tell whether it's high or low is to compare it to a distribution. So these are the possible scores on that active Q test. And that is a distribution of scores in the population, right? So we got scores all the way from 10 to 100. And this is the distribution of individuals in the population and their scores on the active Q. Well, then we can see that Jimmy's score is right there. And it is a high score. There are very few individuals in this population that have scored higher than Jimmy on the active Q, and most of the population scores lower than Jimmy on the active Q. So in this case, 80 on the active Q represents a high score. He has a high level of activity. On the other hand, that same 80 could indicate a low score if this was a distribution, because 80 is right there on this particular distribution, indicating that Jimmy is actually very inactive, right? So his mother's perception of his activity is incorrect. Jimmy is actually much less active than most children in the population. So the meaning of a score takes a lot of its meaning from the context, i.e. the frequency distribution that it's a part of. All right, so let's further take a look at this. So imagine that I still have this active Q, and Jimmy's score of 80 is 25 points above the mean. So the mean here is a mean of 55. Jimmy scores 25 points above that. So he has a deviation of positive 25. And let's say that I also have a test called the ADHD cube, which measures your deficits in attention. And I give that to Jimmy as well. So here's his score on the active cube. And let's say that I give him that ADHD cube, and his score on the ADHD cube is only 70. Once again, the question is that a high score? And the very more complicated question is Jimmy more extreme in his active Q score, or is he more extreme on his ADHD? So is his activity more unusual or more at a higher level than his ADHD? Now, if we were just comparing numbers, it's very easy to say 70 is less than 80, right? We learned that in elementary school. So just by taking a look at the numbers here, you would say, well, he has a higher score in his active Q than he does on his ADHD Q. So the activity is more extreme. That's more of an issue for Jimmy. However, this is a completely different scale. And this is like comparing apples and oranges, right? Two different scales. We can't compare them directly to their numbers. So what we need to do is we need to put them in a distribution, because the idea or the conclusion that Jimmy's active Q score is more extreme than his ADHD Q score is completely wrong if that is the distribution for scores on the ADHD Q. So let's split up the two distributions. Here we have the distribution for scores in the population on ADHD Q. Here we have the distribution for scores in the population on active Q. And you can see in both cases, Jimmy is above the average. In both cases, Jimmy scores higher than most people in that population. But on his active Q, you can see that there is a portion of the population here that scores above Jimmy. However, for his ADHD Q, there is almost nobody that scores higher than Jimmy. Jimmy is one of the highest scoring people in the population on this ADHD Q. So when we put it into this context, we can see that Jimmy is way more extreme on his ADHD Q score than he is on his activity Q. He is way more out there in terms of his attention deficits than he is on his activity. So if we were to identify the more extreme issue, the one that we wanted to start with, clearly once we can see the distributions, it's Jimmy's ADHD that is the higher score and the bigger issue. So once again, it all comes down to we can't directly compare scores on different scales. We can't directly compare apples and oranges. But oftentimes in psychology, we need to, right? Oftentimes we need to figure out what's the most extreme issue. So one way to understand and compare scores is to compare them with respect to a distribution. And what we're going to see today with z-scores is that we're going to compare the scores and we're going to put them all onto a single known distribution, and that is the distribution of z-scores. So that's all that it is that we're going to be doing today. We're going to take scores, we're going to transform them so that they fit on a z-score distribution, and when everything is on the same distribution, we can then compare compare scores to each other. All right, so let's take a look at, we'll start off with z-scores before we take a look at how to compare them. So z-scores are simply a way of transforming your raw scores. So we were talking about the x-scores. Z-scores are nothing different except they're a transformation of the raw scores. So the same way that you would exchange money, the same way that if you were going to Europe, you would transform your American dollars into euros, the same way that if you were going to Japan, you would transform your American dollars into yen, the same way we can transform raw scores into z-scores. So if we had a set of raw scores right here, 8, 7, 8, 11, 9, 8, 11, 6, 4, 3, we can take those raw scores and transform them into z-scores. And what we get out of this, and we'll show you how to do that transformation in just a bit, But we get certain benefits out of this. We get certain characteristics that this transformation does that allows it to be extremely useful. So in general, what this transformation actually does is it takes your distribution and it moves it to a very specific place, and it either stretches it out if it's too narrow, or it squeezes it down if it's too wide. So let's take a look at this. So if we had this distribution here, so that distribution is the scores from this table right here. So if we had that frequency distribution has a certain mean. There's the mean right there. And it has a certain standard deviation. It's got a certain, I didn't make it better. One moment. We'll fix this in post. All right. So it has a certain standard deviation. This distribution is too wide, and the mean is not where the z-score mean should be. So what a z-score does is it just takes that distribution, moves it, so that the mean of the z-score distribution is always 0. So it'll take whatever the mean is, and it'll move the distribution so that the new mean is 0. And it'll, in this case, squeeze the distribution so that the standard deviation is 1. So a z-score distribution always has a mean of 0 and a standard deviation of 1. So if we have this other distribution right here, that distribution has a certain mean. And if we transform these raw scores into a z distribution, it will move it so that its mean is at 0. And in this case, it stretches out the distribution so it has a standard deviation of 1. We got this distribution here. There's its mean. If we transform those scores into z-scores, it will move the distribution so that it has a mean of 0. And it'll squeeze it in this case so it's got a standard deviation of 1. And this is what a z-score transformation does to any set of raw scores. So again, we have these raw scores here, this distribution. There's the mean. If we transform it into a z-score, it will move the entire distribution so that the mean is now equal to 0. And it'll squeeze it down so that the standard deviation is equal to 1. So that's what a z-score does. And as you can see, it's much like, again, exchanging money. Because you can see here that in this case, a raw score of 8 gets changed into a z-score of 0.19. Another raw score of 8 gets changed into a z-score of 0.19. Another raw score of 8 gets changed into a z-score of 0.19. So every score gets changed into a specific z-score. And what this transformation allows us to do is that it allows us to specify where any raw score is within a distribution very, very quickly. So the way that it does this is that a z-score always consists of 2 parts. The first part is the sign, and the sign of a z-score, because the mean of a z-score is 0, so when you have a set of z-scores, because the mean of those z-scores is equal to 0, if you have a positive z-score, then that z-score is above the mean. If you have a negative z-score, then that z-score is below the mean. So if somebody came up to me and said, oh, I scored 11 on my quiz, I would say, I have no idea how you did. Is that 11 out of 12, 11 out of 20? Is that 11 out of 12? Did you do better than other students? Did you do worse than other students? I have no idea what a score of 11 is. But if they tell me, oh, I got a z-score on my quiz of 1.33, I can say, congratulations, that's higher than the class average. And I don't have to know anything about the quiz. As soon as they tell me z-score is positive, I know they scored above average. As soon as the z-score is negative, you know the score is below average because z-scores have, when they're transformed, a mean of 0. So right off the bat, you can see that we already have information here in terms of whether the score is above the mean or below the mean. The other part of the z-score is the number, so they actually come with values. And the number tells you the distance of the score from the mean, right, or the deviation, in terms of the number of standard deviations. So that's a little bit more difficult to kind of wrap your mind around. But what these numbers here mean are standard deviation steps above or below the mean. So for example, a score of 6 is about half a standard deviation below the mean. A score of 11 is 1 1/3 deviations above the mean. So not only do you know that it's above or below the mean, but it's scaled to standard deviation steps that lets you know how many standard deviation steps is it below the mean. In this case, 1 1/3 steps below the mean. How many steps is it above the mean? In this case, is about 19% of a standard deviation above the mean. So the z-scores tell you all that information in one z-score. So again, if somebody said, oh, I have a z-score of 2.5, you can say, wow, you're above the mean, and you are 2.5 standard deviations above the mean. It gives you a lot of information in that one little number. All right, so that's what a z-score is. For the calculation of z-scores, there's a formula for calculating your z-scores. So for a population, the formula for a z-score starts off with the deviation. So when you're transforming each z-score, you take the raw score and from it you subtract the mean. And then to scale it to standard deviation steps, you divide it by the standard deviation of your population. So this is the formula for a z-score, and you can see that it uses the mean, it uses the idea of deviations, and it uses the idea of standard deviations. So it takes the deviation, the score minus the mean, and then divides it by the standard deviation. So that's for a population. For a sample, it's the exact same idea. You take the raw score, subtract from it the mean of the sample, and then divide that by the sample standard deviation. And that's how you go from these numbers here to these numbers here. All right, any questions so far on z-scores? All righty. So we already alluded to a few of these, but let's take a look at some of the properties of z-scores that make them so valuable. So one of the first ones is that they are transformed scores. So why is it that transforming this score just makes it so much more useful to us? Well, the biggest thing about z-scores is that each z-score tells you exactly where you are in the distribution. So each z-score tells you exactly where you are in that z-score distribution. So a raw score of 80 tells you nothing. You don't know if you're above the mean or below the mean. But a z-score of -1 tells you you are below the mean and you are exactly 1 standard deviation below that mean. So the z-scores, they form what's known as a standard distribution. And because they are a standardized distribution, because they all have a mean of 0 and they all have a standard deviation of 1, that means that you can transform any score into a z-score and then compare it to any other score that got transformed into a z-score. So for example, just to kind of go back to that monetary example, if somebody was saying that they own a business, let's say that 2 business owners were having a competition in terms of whose business was worth more. And one business owner, they say, well, my business is worth 8 million euros. And the other business owner says, well, my business is worth 500 million yen. How do we know which one is worth more, 8 billion euros or 500 million yen? Well, one way we can do it is to transform them into the same measure. Transform them both into US dollars, and then you can directly compare the two. So you can't compare yen to euros directly, but if you transform them both into a standardized distribution, then you can. Same thing with z-scores. You can take scores on an exam and scores on a quiz, can't compare them directly, but if you transform them both into z-scores, you can then compare those two different scores. So let's take a look at that, how that might work. So let's say that you finished your education here, you become a school psychologist, and a student comes up to you, and they don't know, you're working in high school, they don't know what they want to do with their life. So you ask them about their classes, you ask them about what their aptitudes are, and they say, oh, I took a class in math, and I just had a quiz, and I got a 7 on my quiz. So that's the distribution of the math scores. There's the 7 on the math quiz. And you go, all right, what about your other classes? And they said, oh, I also had a quiz in English, and I also got a 7 on my English quiz. 7 on the math quiz, 7 on the English quiz, 2 different quizzes, can't compare them. At this point, don't know which one they're doing better in, don't know which class they're doing better in. But if you take those 2 scores and transform them into z-scores, so if you take the math scores and transform them into z-scores, that 7 is right there. And you can see that in math, they're actually below 0, meaning that their score was below the mean. You transform their English scores, and 7 becomes that score right there, and you can see that that score is actually above the mean. So once you transform them into z-scores, you know that this student is doing better in English than they are in math, so therefore maybe they'd want to pursue something in the English language area rather than pursuing a mathematical degree. And again, you can make that comparison, but only after transforming the scores into the standardized distribution into these z-scores. All right, so other things about z-scores, the properties that they have. This one is, the first property is that the shape of the z-score distribution stays the same as the raw distribution. So when you take a z-score, when you take raw scores and you change it to a z-score distribution, you're not changing the shape of the distribution other than stretching it out or squeezing it in. So if it is symmetrical, your z-score distribution will be symmetrical. If it has 2 peaks, your z-score distribution will have 2 peaks. If it only has 1 peak, your z-score distribution will have 1 peak. So the shape of these distributions, when you transform into a z-score, stay the same. They just get a little stretched out or a little squeezed in, depending upon how wide or variable they were to start with. All right, other properties. These are the important ones. Z-scores always, always, always have a mean of 0. So that is regardless of what raw scores you started with. The z-scores will always, always, always have a mean of 0. So if you're ever talking to somebody and you say, oh, I'm doing this experiment, and I took all the raw scores from people's measures of IQ, and I transformed them all into z-scores, and the person asks you, oh, what was the average of the z-scores? They don't know what a z-score is, because the average is always 0. So regardless of what scores you have, as soon as you transform them into z-scores, the average of those z-scores is 0. So we can see here, transformed, average is 0. Here, transformed, average is 0. And that has to do with the fact that your z-scores begin with a deviation in the numerator. So remember that when we added up the deviations for any distribution, it always ended up summing to 0. Same thing here. You add up all the z-scores for a distribution, that will always add up to 0 because the first part of a z-score is that deviation, that score minus the mean. All right, so that's one of the big properties. They always, the mean of z-scores always equals 0. The other big property is that the standard deviation of a z-score distribution is always equal to 1. So it doesn't matter what distribution you start out with, your z-scores are either going to get squeezed together or stretched apart so that the variability, the variance, and the standard deviation of your z-scores is equal to 1. And that has to do with the fact that all the deviations are scaled by dividing by the standard deviation. So if they're really wide to begin with, they're going to get divided by a large standard deviation, and they're going to get squeezed down. If they're really small to begin with, the standard deviation is really small to begin with, it's going to get divided by a small deviation and stretched out. So the standard deviation is always equal to 1. So remember that on z-scores, mean always equal to 0, standard deviation always equal to 1. All right, calculation of raw scores from z-scores. So we saw the formula of how you go from a z-score to a raw score. And now we're going to see how you go from a z-score back to a raw score. So sometimes, if you're a statistician and people are telling you z-scores, you love it because z-scores are so useful. But sometimes when you're communicating with people who aren't statisticians, they want that score again, right? They want that raw score. So, you know, if you're telling your parents how you did on an exam, maybe on the stats exam, and you tell them, oh, my z-score on the stats exam was 1.75, they might look at you with a blank stare and say, I don't know what that means. They want the percent. They want you to transfer it back into a percentage. So how do you go from a z-score back to a raw score? Well, you use the same equation that we saw for a z-score. So equations for a z-score, there it is for a sample. If you want to retrieve the raw score, we just do a little bit of solving for the raw score. And we get to the raw score equals the mean of your distribution plus the z-score times the standard deviation of your distribution. So whatever your original distribution was, if you want to recover a raw score in your original distribution, you take the mean of that original distribution and to it you add the z-score, which is the steps of the standard deviation, multiplied by the standard deviation. So it's literally like start at the mean and then take z-score steps, z-score number of steps, and the standard deviation is how big those steps are. So that's how you get the original raw scores from the z-scores. And then the last thing that you can do with z-scores, at least in this intro to z-scores, is to create a standardized distribution. So sometimes you don't want to deal with the raw scores. You don't want to deal with the z-scores. You want some new distribution that is easy to understand. And in that case, you want to create a standardized distribution. And one of the most famous standardized distributions are IQ scores. So IQ scores are very, very complicated to score, but they have been standardized so that the average IQ score in the population is 100 and the standard deviation is 15. That did not happen by accident. Somebody said, for my IQ scores, I want them to be standardized so that the mean is 100 and the standard deviation is 15. And the way that was done is by using z-scores. So there's two steps for creating a standardized distribution. What you do is you start with the original raw score and you transform it into z-scores. So that's the first step. You take your raw scores, you transform it into z-scores. So if you have your raw scores over here, you transform those into z-scores, and these z-scores here now have a mean of 0 and a standard deviation of 1. Once you have those new z-scores, you then take them and transform those z-scores into new standardized raw scores that have a specific mean, a mean that you've chosen, and a specific standard deviation, a standard deviation that you've also chosen. So that's the key here. It's a new set of scores with a new mean that you wanted and a new standard deviation that you wanted. So when the IQ developers got all of those scores from their IQ raw scores, and they were like 1,011, 952, 1,281, 756, ... They said that they wanted these to be standardized to a mean of 100 and a standard deviation of 15. So what they did was first they transformed them all into z-scores. And I don't, 1.01, that's not going to make sense, 0.95, whatever it might have been. All the z-scores, they transformed them. and then they transform them into their standardized scores. And the important thing to remember here is that the standardized scores need a new mean. So they literally said, make that new mean 100. Make these, change these, so that the new scores have a mean of 100, and change them so the standard deviation is equal to 15. And that's what they did for the standardized scores. So you take your z-scores, you transform them into your new standardized scores using that equation. Your raw score equals your new mean plus your z-score times your new standard deviation, and that's how you come up with these new standardized scores. All right, so that's a lot of stuff to take in. What we're going to do right now is we're going to see how to actually do some of this stuff with a practice Excel sheet. So if you haven't already, open up your Canvas account, take a look in the files. You should find the January 29th, Chapter 2, Z-scores. No, it shouldn't be instructor version, but anyways, it's in there. Take a look for it. What you're looking for is this one right there. So we're going to go through and show you how to calculate z-scores, and I'll show you a sort of technique that you can use to do it very easily and very quickly in Excel. So while people are opening that, I will just make sure that the screens are recording what I want it to record, and we will start in just a moment. All right, here we go. Okay, so this is once again a practice sheet so that you can practice your, in this case, calculation of z-scores. And there's a number of different ways to do this, the calculations I'm going to show you. But this is a way that I find to be very straightforward and will get you very quickly to be able to calculate a whole series of z-scores. So we got question number 1 here, and it goes, given the following sample of 10 scores, for each individual score, calculate the following. We want to calculate a z-score, and we want to calculate a new standardized score with a mean of 40 and a standard deviation of 10. So here's our raw scores over here, and we want to calculate a z-score. We want to calculate z-scores, so we want to transform these raw scores into z-scores. Now, if you recall the formula for z-scores, let me get that up here. So your z-score is going to equal your raw score minus the mean, and all of that divided by the standard deviation. So what we can do is we can right off the bat calculate the mean, and let's calculate the standard deviation. So hopefully you remember how to do these. If not, for the mean equals average, open parentheses, highlight those scores, close your parentheses, and we have the mean for the raw scores. And then for the standard deviation equals STDEV. This is going to be just straight STDEV because we're dealing with a sample, so we're not going to use .p. We're going to use STDEV. We're going to highlight our raw scores, and now we have our standard deviation. All right. So what I'm going to do now is I'm going to show you the way not to do it, and then I'm going to show you the way that you can do it. So don't type in what I'm about to do. This is just to show you why we can't use a certain strategy. All right. So it's very difficult to calculate z-scores directly in Excel using this formula. So we take a look at this formula, and we see that it has the raw score. It has the mean, which we just calculated. It's got the standard deviation that we just calculated. We have all the information there to use this formula. So we could say, all right, equals, highlight your raw score, minus, highlight your mean. We put those in parentheses because this part has to be done first. And then divide that by your standard deviation. And we get a mean score for this first one of 1.75. We pop that into our z-score answer cell using the equals function. We scroll on down and we see that we've got that one correct. So we know that we've done it correctly. So we might say to ourselves, all right, we just want Excel to keep doing that, right? We've done it for one formula, we can do it for the rest. So let's just copy and paste this down, and you can see that Excel is having none of it, and everything goes horribly, horribly wrong. So why doesn't this work? Well, it doesn't work because we set the formula up wrong in Excel. So we told Excel, look one cell to the left. That's where you're going to find your raw scores. And then look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cells down. That's where the mean is. And look 12 cells down. That's where your standard deviation is. And when we copied and pasted, Excel did exactly that. And it went over here to look for the raw score, and that's where the raw score is. But look what happened when it tried to grab the mean. It missed, and it grabbed the standard deviation instead. And then when it tried to grab the standard deviation, it missed, and it tried to divide by 0. And that's why we're getting this hashtag divide by 0 with the little exclamation point at the end. And it's all caps, so you know Excel is yelling at you. But it says, you know, divide by 0. I can't divide by 0. So something went really wrong when we used that copy and paste. But we definitely want to use copy and paste. We definitely want to be able to use that power of Excel. So what we're going to do is we're going to do what I call setting up parallel structures so that we can copy and paste. And we're going to do what I call the cascading waterfall of equals. All right, so what we want to do is we want to set up what I call parallel structure. And what parallel structure is that you have all the information that you need in a single row. So that's a very straightforward way to take advantage of copy and paste if you have all the information that you need in every single row. So what we're going to do is we're going to set up a column of means, and we're going to set up a column of standard deviations, and we're going to use that to calculate out our z-scores. Now, we have already calculated the mean of the raw scores. So using the equals function, we're going to pop that up into the first row of our cascading waterfall of equals. All right, so we put it up into the first row, and we have a mean of 15.2. Now notice once more that we can't copy and paste this down because it will continue to search for that mean, but it'll miss it, right? So every row that we go down, Excel goes down a row from where it's asking. So even though we can't copy and paste that one down, what we can do is we can go to column number 2, row number 2, and we're going to use the equals function, and we're going to make that row, and this is the key part, we're going to make that row equal to the row above it. All right, so we're going to make that row equal to the row above it. We hit enter, and now we have the mean for that row. So on the third row, we're going to make that row equal to the row above it, and now we have the mean for that row. And the reason why this is a time saver is because now you can take that equation that says make this row equal to the row above it, and you can copy and paste that all the way down, and you now have an entire column of means that are accurate. So what we've done is we've literally said for row, how many do I got here? For row 10, make row 10 equal to row 9. Row 9, make it equal to row 8. Row 8, make it equal to row 7. 7 is equal to 6. 6 equals to 5. 5 is equal to 4. 4 is equal to 3. 3 is equal to 2. 2 is equal to 1. 1 is equal to the mean that we calculated. When we double click on 1, we see that it's equal to the mean that we calculated. So once we put that in, we have this cascading waterfall of equals that fills our entire column with the mean of 15.2. We can do that with the standard deviation as well. You make the first row equal to the standard deviation that you calculated. You then make, and this is the key, you make the second row equal to the first, and it's that second row that gets calculated, that gets copied all the way down, and you get this waterfall of standard deviations because you're making each row equal to the row above it. All right, so that's the first two moves in calculating the z-scores. You're going to make one column of means using that cascading waterfall of equals. You're going to make another column of means using that cascading waterfall of equals as well. All right, so does everybody have these two columns? Okay, so now that we have our row of means, sorry, our column of means, we have our column of standard deviations, now we're ready to enter in the formula for the z-scores. So once again, we go equals, open parentheses, because the deviation has to be done first. We highlight where our raw score is. From that, we're going to subtract. We highlight where the mean is, and then we divide by the standard deviation. And this is a nice kind of place to point this out. Sometimes if your formula gets too large, Excel will not allow you to click on the cell that you want, but you can always get there with your arrow keys. So if that ever happens, just move your arrow keys around. You don't have to go on this wild of a journey, but just get it to where you want it to go. And then you hit enter, and we have our z-score calculated. We're going to update our equals with this z-score that we have here, and we saw that we got that one correct. So we've entered in our function for the z-score. Now we can take that function and we can copy it and we can paste it down one row, and we will still get the correct z-score. And the reason is because all the information that we need for those z-scores are on the same row. So when you go down one row and tell Excel to look left, Excel still sees all the information that it needs. And when you tell it to go down another row and look left, it'll still see all the information that it needs. So if we double click on this pasted formula, we can see that it's still grabbing the right raw score, and it's still grabbing the mean, and it's still dividing by the standard deviation. So we have set up this parallel structure where we can copy and paste all the way down, and we can calculate our z-scores very, very quickly. All right, so once again, this works because you have the information that you need for each z-score in every single row. And then when you copy and paste that formula, you go down one row. All the information that it needs is still located in that row. All right, question? All right, so we could, in this case, put fill our answer cells here with that equal function and transfer all our z-scores. So make sure that you're using the equal function because these z-scores are going to have a ton of decimals. And we want to make sure we're as exact as possible and we're carrying all those decimals with us. And in this situation, we can check down here and see in the green answer cells that we've gotten all our z-scores correct. But let's say that this was the real world, or coming in about a week, your exam. How could we double check our z-scores just to make sure, just to give us a little bit of extra confidence that we calculated them correctly? In other words, what are two things that we know z-scores should have? A mean of 0 and a standard deviation of 1. So when you're calculating z-scores, one of the things that is a great kind of habit to get into is to just use your functions and calculate the average, highlight your z-scores, hit enter, and you will get in Excel a number like this. This is scientific notation. This means 1.7 times 10 to the minus 16th power. That equals 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 7. That's close enough to 0 for me. Okay, so if you see that 1 point something something to the exponent minus 16 or minus whatever, that's your indication that it's extremely close to 0. It's just rounding off errors. Calculate your standard deviation equals ST/DEV. Open your parentheses, highlight your z-scores. Excel's being way more friendly on this. We got a standard deviation of 1. So that's your double check, especially in a real world or exam type situation, to make sure that there wasn't any slip of the finger, there wasn't any, misstep anywhere along the way. You calculated a set of z-scores. You know the mean should be equal to 0 if you did it correctly. You know the standard deviation should be equal to 1 if you did it correctly. 2 seconds to just double check it with equals average and equals ST/DEV. And we got ourselves a little bit more confidence that we did it correctly. All right, so that was part A. That was the z-score. Part B here is asking you to come up with a new set of standardized scores that have a mean of 40 and a standard deviation of 10. So we're going to set up another column here called StandX for standardized scores. And we are going to use the formula that a score equals the mean plus your z-score times the standard deviation. So we want to use our z-scores to get raw scores. So this is the function that we need, the one that gives us those raw scores. When you're doing a standardized score, what I find trips up students the most is knowing which mean to use and which standard deviation to use. And for a standardized score, those are the ones that are given to you, and they will be given to you in the question. So the question 1B says, we want new standardized scores that have a mean of 40 and a standard deviation of 10. So this mean here is going to be 40. This standard deviation here is going to be 10. And the z-scores are going to be the ones that we calculate. So now we can use Excel and we can say, all right, we need to pop this equation into Excel. So it's going to equal the mean. Since that's given to us, we can just type in 40. So the mean is 40. We're going to use 40 for the mean. Add to that your z-score. We highlight the cell with the z-score in it. Multiplied by, that's the asterisk, your standard deviation. We got to go back to the question and see that our standard deviation is 10. Once again, equals the new mean that you want. Add to that the z-score multiplied by the new standard deviation that you want, which is 10. And then we can copy and paste that all the way down. And we can enter that into our standardized score answer cells and see that we got those ones correct. And Excel will sometimes, rather frustratingly, not show you the full decimal places. You can always go on your Home tab. If you see these two buttons up here, one of those will increase your decimals, one of those will decrease your decimals. So if you like seeing those extra decimals, you can do that to your heart's content, but however many decimals you want. But if you're using the equals function, rest assured your entire answer is in there. All right, so we scroll down, we see that we got all those correct. But let's say one more time that this was a real world scenario, or this is your exam, and you will be calculating standard scores on the exam. What is a way that we can test whether we calculated the standardized scores correctly? So what do we know? In other words, the mean of the standardized score should be, and what is the standard deviation of the standardized scores? So what does the question say? 1B, what should our mean be? 40. I heard a whisper on the wind of 40. All right, so yes, it's supposed to be 40. They asked us in question B, make a new standardized score for me. Make a new set of standardized scores, and I want the mean to be 40. So let's check to make sure we did that. Equals average open parentheses, highlight your new standardized scores, and we see that we have, in fact, an average of 40. We got that part correct. We also know that we were asked for a specific standard deviation. Specifically, they wanted a standard deviation of 10. It says so in the question. They said, make me a new distribution, and I want the standard deviation to be equal to 10. So we highlight the scores in our new distribution, STDEV, to calculate a standard deviation, and we find out that we got a standard deviation of 10. So once again, this is just a way to double check to make sure that there wasn't a slip of the finger anywhere, to make sure that you didn't put in 4 instead of 40. It's just a way to double check your distribution so that you have more confidence that you've done things correctly. All right, so questions like this will be on the exam where you're calculating a z-score and you're calculating a standardized score. So I would highly recommend give question 2, 3, and 4 a try. Try to use the copy and paste. Try to use that cascading waterfall of equals. And let me just wrap up what I want to make sure everybody is aware of. So let's just go through this, and then anybody that has questions, I'll come by to give you a hand. All right, so homework assignment number 5, chapter 2, part 3. This is going to be uploaded to Canvas. So it's an Excel file that you can find in Canvas, and you are going to upload, you're going to complete that Excel file and upload it to Canvas assignment. Now the due date has been changed. That's going to be due tomorrow by midnight. So it's very much like what we just did in class. So download that from Canvas, complete the Excel sheet, and then re-upload your completed Excel sheet to that assignments tab. So it's not a MyLab assignment. It's specifically one of our only 2 Excel file Canvas assignments. For this, very important, you're going to be asked about samples. So use sample variance and use sample standard deviation as well. For the Chapter 2 post-test, that is going to be due Monday, February 11th at 12:45 p.m. Double check the syllabus, please. I wasn't able to update these slides here, but double check the syllabus for the new due dates. Make sure that they don't catch you unawares. And also, I have updated your grades in Canvas for your 2 pre-tests that we've done to reflect your mastery points that you have accumulated. So there is still time to accumulate those mastery points for both pre-test 1 and pre-test 2. They are due midnight before exam day. So if you haven't already taken advantage of that, please do get yourself 100% on those 2 pre-tests. Get yourself that extra practice that you need. All right, so that's all that I wanted to cover for today. So anybody that has questions, I will come by in just a moment. But I do believe we are very close to the end of the class. So that will be it for today.